Our next speaker is Bick. He's an associate professor at the Vrije Universiteit Amsterdam, and he has so many affiliations that I usually forget. Oxford, TUM, Munich, Exeter. Do you have others?
No, not that I'm aware of.
And yeah, and he loves graphs and hypergraphs so much that recently convinced two people to join him in creating a book for children about graphs and hypergraphs.
I'll mention more. Thanks very much. Thanks very much, Rafaela, for the kind introduction, and thanks to all the organizers for inviting me. I'm very happy to be here. I'll talk about well, network interactions and effective interactions, and some more at the end. Well, where's Ben? He left. Oh no, just wanted to point, he said at the beginning, well, he doesn't know a lot about hypergraphs, me neither. So I'm very happy to, it kind of just comes up every once in a while, but I'm also very curious to understand more about kind of the combinatorial properties of hypergraphs, because they come up in various scenarios that I'll talk about as kind of useful combinatorial aspects, like to capture interactions in network dynamics. So that's kind of my background. Before I start, I just want to acknowledge the collaborators. I'm very happy that Jürgen already mentioned the work by Toby Bölle, PhD student that was on a joint project with Christian and myself. I'll also mention some more recent work with Bob Rink and Babette de Wolf, Babette just moved from the VU to Hamburg, and towards the very end, a little project with Søren, who's in Paderborn. So just to kind of tell you a little bit, or give you the big idea of what I'm interested in general, I'm interested in oscillator networks. So the typical objects of my study are dynamical systems that have, if left in isolation, a periodic oscillatory motion. So if you don't want to think about this in this abstract way, think about pendulum clocks. They swing back and forth, back and forth, back and forth. Right? But oscillatory dynamics don't just come up in mechanics, but also in other scenarios like the brain. We've talked about brain waves and oscillatory signals in the brain, or certain models of power grid networks. So that's each unit in isolation. But what I'm really interested in is what happens when you take multiple of these things and you couple them together. And since I'm now based in the Netherlands, probably the famous experiment is this down here, the two clocks that pendulum clocks that are hanging from the same beam, so they can transfer energy from one to the other. And then Huygens described this strange kind of sympathy between the clocks, so a type of synchronization behavior that appeared there. Synchronization is a common thing also in other systems, such as the brain and so on. But that's the type of systems that I'm interested in. So to kind of like take this to a slightly more abstract level, what I'm interested in is, in general, networks of oscillatory units. So each unit, so that's kind of my blue dot here, is a dynamical system that in isolation has an attracting limit cycle. But they don't exist in isolation, but they form a network, so they talk to each other. So here in my little cartoon, I have these individual dynamical systems, and I have interactions between them. And since they're dynamical systems, there's two main ingredients that govern the dynamics of the entire thing. On the one hand, there's the network structure, or the network topology, so kind of who talks to whom. And on the other hand, there is the network interaction. Also, when you have, well, each node is given by a state. So you have to say, how does the state of one node influence the state of the other node? So you have to specify a little bit more information than just the who talks to whom, but also how does one node influence the other node? And the big general question that you want to answer is kind of, how do the two ingredients together shape the network dynamics, the overall dynamics of the entire network? So that's kind of the general framework that I'm interested in. We already saw the Kuramoto model. Thanks, Dinestra, for introducing this. So, for example, one thing that you can think about is take a Kuramoto model on the network. So you have a graph here. there's pairwise edges. Here's my node K, J, and L. And here you have interactions between pairs of these oscillators. So what does an oscillator mean for the Kuramoto model? The state of each of these oscillators is just given by a phase variable. So basically, you determine what the angle of the cycle is that your oscillator is in. And in Kuramoto or Kuramoto type models, the type of interactions are basically some 2π periodic function that depends on the phase differences. If that's a sine, then you get the Kuramoto model, and the type of dynamics that you might expect. And we've seen this plot here as my own little sketch is this. If this is the coupling strength and you have heterogeneous oscillators, then you see a synchronization transition that is kind of a continuous transition towards synchrony. So first you have disorder, but at a critical coupling strength, some partial synchrony emerges. And if you crank up the coupling strength, then basically in terms of this order parameter R, that's kind of somehow the synchrony in the system will saturate to 1 to be fully synchronized. So higher order networks have become very fashionable. So one thing one can do is say, okay, well, I look at Kuramoto on a graph. That's the old school stuff, and I try to understand what the graph properties affect synchronization properties. But of course, I can also take it to the next level. Yay! I take a hypergraph or a simplicial complex or whatever you like. So that means that now I not only have edges, but I also have faces or something else, and I interpret these kind of higher order, these hyper edges, as something that now gives us nonlinear interactions. So say triplet interactions for triangles between oscillator phases. And that's kind of what Ginestra described as kind of the node-centric view, right? So the dynamical properties just lie on the nodes, and the interpretation now of kind of the interaction functions lies in terms of the type of nonlinear interactions that depend now in a nonlinear way on, say, triplets of oscillator phases. But obviously, here you not only have to specify the who talks to whom, namely what triangle is filled in, but you also have to specify, well, what is an interaction function that corresponds to such an edge, right? So this is one example where, for example, you have 2 times 1 phase minus 1 phase minus another phase. But you could also pick another one, right? So you have to make a choice for these triplet interactions, what kind of interaction function you want to have. And if you do this, and there's this nice paper by Per Skardal and Alex Arenas, you can then study the synchronization dynamics. And one thing that you might see is that instead of having this continuous transition to synchrony, you can do some analysis if you choose your interaction in the right way. And you can take what is here. If you do the right mean field reduction, you can turn this into kind of from a supercritical pitchfork and a subcritical pitchfork, and you get a discontinuous synchronization transition. That's nice. So you kind of have see a new effect in some sense that is given by these higher order interactions. You can do more, you can add lots of terms, and I'm kind of guilty myself in this way. You can find more complicated dynamics rather than synchronization. You can find heteroclinic dynamics, chaos, whatever you like. So depends on like how you choose your 2 ingredients, you can get some complicated dynamics. So that's one way to kind of take the Kuramoto model and kind of generalize it, right? We, rather than having graph structure, you take a more complicated interaction structure, and then you see what the dynamics are. But at the same time, you can relate phase models. So that's kind of basically the idea that the state of each node is given by a phase variable. You can also relate this to somehow coupled nonlinear oscillators. And that's actually the original motivation by Kuramoto as well, that basically he did a reduction of a coupled nonlinear oscillator model because Kuramoto, as a physicist, was interested in the synchronization of actual physical systems, right? So his complicated physical system that he wanted to describe by phase dynamics. So in a nutshell, I'm not going to go into the detail, but there's a way to basically relate phase oscillator models on the one hand to coupled nonlinear oscillators. So how does this work? That's basically just to give you an idea, if you forget about the phase dynamics, say you take your complicated nonlinear oscillators, you uncouple them, right? Well, since you assume that everyone has an attracting limit cycle that is sufficiently nice, what you get when you take n of these, well, an n torus, right? Great, n torus. I have my n torus for the uncoupled system that is in the joint phase space is normally hyperbolic. So general math theory tells you that, well, there exists an epsilon naught such that for any epsilon, yada, 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 there is also an invariant torus in the full phase space. So that basically means that the full dynamics of this thing is described in terms of phase variables, because amplitudes are effectively enslaved by phases, by the phase variables, and the only thing that counts are the phase variables. So synchronization can be phrased in terms of just phases only. Okay, so that's basically what you do, and the main thing is that a phase reduction in some sense is an approximation of the phase dynamics on your invariant torus, right? So in some sense that's a dimension reduction, because your high dimensional dynamical system with possibly complicated oscillations can be just written by a simpler system that is lower dimensional on a non-trivial geometry, because now you have an n torus rather than well, something that might be Euclidean or something like that. But there's basically a translation one-to-one. So just to kind of, I'm just using this as an analogy, but in some sense, it's also not necessarily surprising that you might see the same dynamical effects on that you see here. Well, when you fill in kind of these edges, and you see non-trivials, well, you see some kind of discontinuous synchronization transition, that you see the same thing here. And I'm not saying that there's a clear link between them, but here there's this paper that was published in Science Advances that says first order synchronization transitions in large populations of strongly coupled relaxation oscillations. So that kind of tells me when I read this title is that, okay, well, for strong coupling, say when the higher order terms in my phase reduction become important, I might see kind of the same kind of effect. And that's really the point of the talk, is kind of say, okay, well, maybe the two things are related, and what's the relationship and what can we learn by translating one system into the other system? So, two ways to get higher order interactions. Well, one way could be that you take your coupled complicated oscillators, and you have in your complicated coupled oscillators here, you have pairwise interactions already, and you have triplet interactions, so nonlinear interactions that involve three different states. And then you do an expansion. Typically, you write the coupling strength as your small parameter. You do an expansion in terms of your coupling strength, and you would expect that already to first order. Well, basically, every edge here corresponds to an edge there, and every kind of triplet interaction somehow results in some triplet interaction here, right? So you basically copy the system over. But you can also get triplet interactions. How to do this, you can look at this paper. But you can also get triplet interactions when you then do higher order phase reductions. So when you not only calculate the first order approximation to your phase dynamics, but also the second order approximation to your phase dynamics. So the basic idea is that here you have these coupled nonlinear oscillators that now interact just pairwisely. But when you take the first so the first order terms then correspond to somehow the pairwise interactions between them. They correspond to the edges here. But the second order interactions, they include interactions that are nonlinear interactions between triplets. Why is that? Well, just because this oscillator here, through this oscillator here, also like affects that oscillator. Right? So in some sense, the higher order terms kind of add more, add more of the indirect interactions that you have here. But the idea is now that here, on the one hand, you have somehow, well, complicated oscillators with simple interactions that you can translate into, say, simple oscillators, because you've reduced the dynamics of your phase space with more complicated interactions. So you've kind of shifted the problem from one side, namely, say, the nonlinearity of the individual oscillator, the complicated shape of the limit cycle, into something, well, in isolation, this just evolves at a at a simple, constant speed, but basically you shift all the nonlinearities of your oscillations into the network interactions. But since they're related, I mean, they should reflect the same physical system, right? And that's basically the idea. So that's what I want to focus on. Of course, in full generality, these things, especially the higher order phase interactions, are difficult to compute. So let's focus on a particular class of oscillators where they're particularly simple. So Stewart-Landau type oscillators where your oscillation, your limit cycle is a really nice circle. Right? It's like nice circle. There's some rotational symmetry because basically you can shift the phase of all the oscillators by a constant amount. And then you can calculate the phase reduction. Then you can hope that you can actually calculate the phase reduction for this. So basically the higher order interactions that I'll talk about in the first bit of the talk are basically phase interactions that come through the phase reduction of these type of simple oscillators. But even for simple oscillators, these things become, well, I want to say a pain to compute, right? So there's three specific questions that we looked at. The first two questions joint work with Toby and Christian. And the second one relates to, well, the second set of questions, question number 3, relates to the work with Babette and Bob. So what are the three questions? The first thing is that, okay, well, for these simple oscillators, we have this nice round limit cycle. So, well, one idea is like, let's make it more complicated. We like to make things more complicated, right? So instead of, well, that's a very good question. But that tends to be the tendency. I remember there was a paper not so long ago that it's harder to simplify things in the right way rather than to make things more complicated. But that seems to be the tendency. So the main point is here that we now do a perturbation of our nice sinusoidal oscillator, our limit cycle oscillator, by something that can evolve in some neighborhood. So we do a perturbation in terms of the shape of the limit cycle. So rather than having this rotationally symmetric thing, make things more complicated. This in general works, well, this a priori, the most of the analysis is for all-to-all coupled systems. So the second question we asked ourselves is, so what happens for networks? Third question is like, okay, let's make it even more complicated. Let's add some delays to these interactions. So rather than looking at instantaneous interactions, let's look at delay differential equations where somehow there's a finite speed of propagation, say. Yes?
Sorry, but I don't understand your question 1. How is that more complicated than your simple oscillator? It looks like there's just one.
Also, so basically, well, maybe I should have been more clear. So in this phase reduction that Ivan and Diego did, they looked at these sinusoidal oscillations and they computed these phase reduction terms. So what I'm interested in this particular work is like, can we also do this for more complicated oscillators? So basically, Ivan and Diego did it for Stewart-Landau oscillators where you have this rotational symmetry. Our question was, okay, well, how does the perturbation in shape affect the synchronization dynamics, for example? Okay. So let's go through the questions. So the first question is, let's also look at a, well, not necessarily small parameter delta, but some kind of some shape parameter that changes the shape of the limit cycle. This is the most complicated formula I have there. Please don't remember this, but the main point is that you can compute this. And Toby did this fantastic work that he actually churned through these terms and computed phase reduction that is now something that has an intrinsic frequency, that has some terms that depend on this symmetry breaking parameter delta, and then to second order, that's the first order terms because it has a k. So my epsilon now is called k for the coupling strength, k squared, they become more complicated and you have to do quite a bit of work to compute what these terms are. So so the point is you can write down these expressions. And of course, the question is, well, what does this bring us? Well, the point is it works. So this is now a comparison of how good this second order phase reduction actually is. So on the left-hand side here, this is a stability diagram in terms of the shape parameter. So this is delta here on the x-axis. This is the coupling strength on the y-axis, and you see that you have some kind of synchrony of in-phase synchrony. I think there's a stability of splay phase synchrony. No, sorry. This is the stability diagram for in-phase synchrony. So it's stable here, it's unstable here, and it's stable here. If you just do the first order phase reduction, you get this. So you see the bifurcation line at k is equal to 0. Here it's stable, here it's unstable. So the prediction is quite bad if you want to take it that way. Already at second order, and this is kind of the same stability diagram for the phase dynamics to second order, you basically have in the picture norm. So I'm not quantifying this, but just staring at the pictures, right? You can see that this is pretty good at matching this. And this is kind of a slice through this that already the second order approximates the full system like in a better way. So that's maybe a reason why you would say maybe you should go into second order in terms of these phase reductions. Okay, but they're paying to compute. So it's like I'm grateful to Toby for doing this the computations. Okay, Toby also then looked at well, basically what happens for networks. So when you don't have all-to-all coupling, then you have an additional layer of bookkeeping because you have to well, keep track of what edges you have in your original network and then basically see, okay, well, what kind of second order effects do you have? And the way we quantified this or kind of try to kind of map this out is in the following way. So for the second order terms, you have to look at basically well, either neighborhoods of this target node K of two neighbors, and then you get somehow pairwise interactions between the neighbors. That's what you would expect anyways, right? They're coupled in the physical network, and there's a pairwise interaction of this type between, well, from oscillator A to oscillator K. In addition to this, you also find a kind of weird triplet interaction where there's an effect on oscillator K depending on a pairwise term between I and L, right? So in some sense, this is also a triplet interaction because like even though this doesn't depend explicitly on the phase of oscillator K, it is the term that is in the dynamical equation for the phase of oscillator K. So you kind of have this weird pairwise, non-pairwise interaction. The third type of interaction that you get is a true triplet interaction of this form. So for each one of these motifs, you get a term basically that is a non-pairwise interactions between these two phases onto your target phase. That's the first thing that you have to keep track of. The second thing are basically the two-step processes. So for K connected via L to I, you get a pairwise interactions again between K and L. That's kind of the same thing. But then you also get a pairwise interaction between I and K, right? Whether or not there exists a physical link there. So there's a pairwise interaction in your phase equation, how I affects K. So give it a fancy name, call it a virtual pairwise interaction. But that's something obviously that you don't see when you have an all-to-all connected network, because if you have an all-to-all connected network, then between any two nodes, there's a physical link. So it's just seen as a correction to this link. But here you actually get pairwise interactions between non-physically connected systems. Of course, you also get then the true triplet interactions along basically paths of length 2 in your system. Of course, if you only have two nodes, then these collapse to basically higher harmonics in your interaction function. Because if you have only two nodes, then this motif basically means that K is equal to I, and that means that you have a second harmonic in your interaction function. Yes? Say it again? Oh, this is a phase shift parameter that comes from the dynamical equations that I didn't write. So this is just to indicate that there is an interaction function that corresponds to each one of these motifs. So you can see them as kind of this is the structural bit, but this is the interaction function that corresponds to this edge, hyperedge, and so on. And the alpha relates to particular physical parameters of your model equations that I don't want to go into. The third thing.
have the results for Kuramoto model with direction sinus difference of phi 1 minus phi 2 plus alpha, where alpha is fixed.
So in some sense, so we don't really look at Kuramoto because we look at identical oscillators. So in some sense, Kuramoto always assumes that you have non-identical oscillators for like with intrinsic frequency from a unimodal example from a unimodal. Can't speak. It's the end of the day. Unimodal distribution. So in some sense, the like if you look at synchrony in identical oscillators, then basically your alpha effectively modulates the coupling strength. So that's how it acts.
The strong effect with alpha equal to pi.
But then by alpha equal to pi, then you have negative coupling, right? So then basically you switch your coupling strength from k to minus k. That's alpha is equal to pi. Yeah, exactly. So I mean, you have a bit of dependency between a phase shift parameter in your phase equations. But I'm not talking about phase shifts in the phase equations. I want to link them to the physical parameters. So this alpha that I mentioned there, something that you can compute from the physical parameters of your oscillator model. But I'll come to this again in a second. Any other question? Yes. Oh yes. Say B3, B.
B1 and B2.
This one. So
The argument for sine in both include only nodes that aren't connected, but the diagrams show different.
But so this one, yeah, they aren't connected, but this is an interaction from I and L to K. So it's really a triplet interaction. This is an interaction involving phase phi I, and phase phi k onto phase k. So that's a pairwise interaction. That's the difference. Does that make sense? Cool. Okay. Just a brief word of what happens for delays. I won't go into the details, but obviously coming back to this phase shift parameter alpha is typically associated with a delay. The question is whether you can do this explicitly, this phase reduction for delay coupled oscillators. So what we did in the work with Bob and Babette is that we take two simple delay-coupled oscillators, which is a nice infinite-dimensional system. So yay, let's make it a little bit more complicated. And then we do a phase reduction. And going to the right spaces basically still means that if your coupling, if your delay is just in the coupling, you can also do in the right space a reduction to a finite-dimensional torus by the same kind of argument. So finish your theory for basically infinite-dimensional phase spaces. So that the idea is that even though your system is infinite dimensional, you should have dynamics restricted to finite dimensional torus. Okay? And that's really nice because like for your infinite dimensional system, your phase reduction is actually finite dimensional. That's quite nice. So like the point is from a mathematical point of view, any kind of Kuramoto with delay is not the right kind of phase approximation that you should have for these types of systems. How good is this approximation? So this diagram kind of summarizes well, how well you can use a one-dimensional system to approximate this infinite dimensional system. The color coding is stability of synchrony in the infinite dimensional system. And what I want to approximate is the bifurcation line here, right? So where the blue turns red. So when things don't go to in-phase synchrony. To first order, that's what you get. That's the phase shift approximation where you basically, instead of having delay, you substitute by phase shift. That's pretty bad. Already to second order, you get a quite nice approximation. So this is for, well, coupling strength as 0.1, so it's not vanishingly small. But here you basically find in terms of your delay, that's the delay parameter, that's basically approximates your stability regions actually quite nicely. And this is computed, these lines are computed from a one-dimensional equation, right? That's a one-dimensional ODE. So in some sense, at least for these kind of simple systems, it works well for stability analysis of a stationary state in this infinite dimensional system. Of course.
Yeah, but delay, relation with delay on one dimension is somehow intrinsically infinitely. Or you need sort of
So there's no more delay in,
conditions. Okay, just generally. Then because of that delay, equations with delay are much more complicated.
but there's no delay in the phase equations. So there is really a one-dimensional ODE where I compute all the parameters of my Fourier harmonics.
Reduction, you have just order.
Exactly. So that's the main point. So I've really kicked out the delay because the mathematical theory basically tells me that the right object to have is an invariant torus that has an additional symmetry. So I can, instead of having two phases, I can kick out one phase in a normal form because it still has a normal form symmetry up to any order. And it's a true one-dimensional thing where now the delay feeds into the parameters of my, my phase equations. And the question is how. We've done this for two oscillators, yay. It's a little bit more algebra to do it for multiple oscillators, but I expect that very similar kind of coupling terms come in here. What these are, I don't know, because we've only computed this explicitly for two oscillators. But I expect that then basically the coupling delay will come up as just as a parameter in my finite dimensional system. Why do I mention this? I think there's an opportunity there to kind of learn a little bit more from the people who know about hypergraphs, because somehow I started off with a graph. I deduced some hypergraphs or a collection of hypergraphs that correspond to my higher order interactions. And I know something about synchrony in my full system. Maybe this relates to, and I'm speculating here, this is what I want to learn, about the spectral properties of the collection of hypergraphs that I get by representing my nonlinear system in a nicer way. So that's kind of what I hope to get in the long run, that somehow certain properties of the couplings, of the effective coupling structure, somehow reflect the synchronization behavior of my nonlinear system. Okay, how much more time do I have?
10 minutes, including questions.
Okay, then I'll briefly talk about something actually interesting. So it's like I've bored you enough with all this kind of boring phase oscillator stuff. You kind of have dynamical systems on an invariant torus and so on, and you can make things more complicated. But then in the end, we only talked about synchronization and that kind of these kind of boring dynamics. One little hobby thing of mine is to look at a little bit more global dynamics. So for example, heteroclinic dynamics. So in the easiest case, heteroclinic dynamics are given by basically a collection of equilibria. They are of saddle type, so they have stable, unstable manifolds, and they meet. So that there are trajectories that basically in forward time go to one equilibrium and backward time go to the other equilibrium. Well, you can bore me, you can give me questions about where this is used in neuroscience, computation, whatever, you name it. The main idea is that this is not just local analysis of local stability around a state, but in order to have this, you kind of have to have the local dynamics have to match up and the global connections also have to match up. And then you can have trajectories that spend some time close to one equilibrium, then switch over to the other equilibrium and so on. And then you kind of have some metastability between quasi-stationary states. So what did Søren and I do? We looked at heteroclinic dynamics, or whether heteroclinic dynamics can emerge in dynamical systems on specific hypergraphs. So we took now, yes, I do know a little bit about hypergraphs, but I'm kind of picking my my favorite models. So I take a hypergraph that is directed. And that's kind of my definition. You can argue about this definition, so that my hyper edges have a tail set and a head set. So some kind of source nodes and some kind of target nodes of n vertices. And again, you can argue with this. I call H undirected if the tail set and the head set is the same. So because you can then have an analogy to just undirected hyper edges, which in some sense means that every target is also a source. Right, and then you take your state xk, and if you say it evolves according to some intrinsic dynamics plus some coupling term that might depend on the edge, where basically, well, it's affected by like every edge such that k is in the head of the edge. So there's an edge that points towards k, given by the coupling term that is specified here. Then you kind of get a general model of a hypergraph dynamical system. Again, the nodes, like the dynamical units, are the vertices the nodes of the system, and the hyperedge specifies like the interaction type that you have. Examples we've seen before, basically. You can see the phase reduction as something that comes out of this. And this kind of is a general enough model to cover quite a number of things that have been published in the literature as kind of dynamics on hypergraphs. So we said, okay, well, let's focus on the emergence of heteroclinic dynamics. Can heteroclinic dynamics emerge depending on whether, say, the hypergraph is undirected or directed, whether the coupling GE depends on the edge or is kind of homogeneous, say in the order, you only have a coupling function for each order of the hypergraph, whether the hypergraph is uniform, so that there's only hyperedges of a given order there. We've seen this. But the main thing is, like, can we find obstructions that heteroclinic dynamics come about? And the main reason for this, let me just finish, is that this is now a global property. So before we mostly talked about synchrony, which is kind of a more local property. So you have a particular synchronization manifold. You want to understand stability of this manifold. Now we have basically multiple states at different spots in phase space. In order to have a heteroclinic cycle, you have to make sure that the linear stability of these different states have the right stability properties, that you have unstable dynamics in this direction, stable dynamics in that direction, and that you can have a heteroclinic connection. So it's a little bit more of a complicated problem. Yes, Heather.
Sorry, maybe missing something. I'm trying to understand. So to test something is heteroclinic for a network, what's the test, or how are you determining it? Or do you actually have to, if it's sorry, you maybe said
I'll go into how we test this. So we basically, that's thank you very much. That's the next slide. So we basically look at two examples. Like you look at the literature and you say, okay, well, how do I test this? There's like many ways to get a heteroclinic cycle. Let's pick out two prototypical scenarios of heteroclinic cycles. The first one is to the left. That's the famous Guckenheimer-Holmes cycle, where you have three equilibria that sit on these coordinate axes. You have that the planes are dynamically invariant, and you basically have a saddle type connection here, a saddle sync connection in these invariant subspaces. Right? That's the famous structurally stable heteroclinic cycle published by Guckenheimer-Holmes a while back. That's the first example that we looked at. The second example is an example of a construction of a heteroclinic cycle or network. So some people have wondered, given a graph, a directed graph, can I write down a dynamical system that has this graph embedded as a heteroclinic network in phase space? And they construct this, and one construction is the following. You take a number of dynamical variables, you look at the diagonal where they're all equal, you construct your vector field such that basically you place basically all the nodes of your graph as equilibria on your diagonal, and then you find invariant two-dimensional subspaces that all intersect the diagonal in which the connections lie. That's a general construction, and you can use this to construct heteroclinic cycles, networks, and so on. And this is like the smallest one of these that you can think of. You have two equilibria that lie on the diagonal. You have one invariant subspace that is S3, where basically this one is connected to that one, and that one is connected to that one in S2, which is another two-dimensional invariant subspace that intersects the diagonal. Okay, that's neat. But now you can already see what the problems are. Because if you have a dynamical system that is on an undirected hypergraph, you would expect that there is some symmetry properties, because somehow the undirected hypergraph means that you have with an undirected hyperedge, you have that every node in this hyperedge is affected by every other node in the hyperedge in the same way. Right? So that's kind of the natural assumption that would come through this combinatorial structure in this framework I had before. And that gives you obstructions, because if you have the symmetry, then basically this diagonal, which is the space of full symmetry, full isotropy, can only have stability that is points in the same direction everywhere, transverse to this. And yeah, so it's either well, stable or unstable. So you can't have anything of this type where basically this is unstable in this direction and stable in that direction, because symmetry forces that it's stable, either stable in each direction or unstable in each direction. And that's the type of results that we kind of try to map out. So what are the lessons that we took from this? There's some obstructions to realizing this as a dynamical system on a hypergraph. So if you have undirectedness, then, for example, you cannot realize the Guggenheimer-Holmes type of cycle because of like restrictions on how you can choose the stability of your equilibria. You can't have that basically this is stable in that direction, this is unstable in that direction, stable in that direction, and so on, because here you need a cyclic symmetry rather than a full permutation symmetry, which is something that in this framework undirected hypergraphs would imply. You can do the same thing for this other construction, and then you can also give some positive results that basically the Guggenheimer-Holmes cycle can be realized on 3 uniform hypergraphs, but not on 4 uniform hypergraphs, because on 4 uniform hypergraphs, again, you have, well, less hyperedges and more dependencies. Right? So we mapped this out a little bit, and basically the bottom line of this is that depending on what global dynamical phenomena you want to construct, you have to see, well, what kind of combinatorial object is the right object that gives you enough freedom to well, construct certain global dynamics. I don't want to bore you much longer, but the main idea is that well, for the first part, that phase oscillator dynamics, on the one hand, can be seen as models per se of oscillatory dynamics, but importantly, they can also be linked to real-world nonlinear oscillations. And I think it's very important to keep in mind that if you generalize your Kuramoto system in a particular way, that might actually correspond to a nonlinear oscillator system that has this phase reduction, especially if you think about strongly nonlinear oscillators or stronger coupling strength and so on. So that gives an opportunity, in my opinion, to translate results of hypergraphs of these effective interactions to the physical systems that might be simpler coupled. They, well, give good approximation for the dynamics, but this kind of idea of directedness is important. I think that if you look at dynamical systems on these hypergraphs, then often enough you want to have directedness in order to get interesting dynamics. Of course, there's many other questions, but that's kind of some takeaways that I want to give you along the way. There's some positive news. There's more to come. And I invite you to participate. So we have a new doctoral network where most of the hiring is done now. We're officially going to kick off in the fall. And I'm very happy that quite a number of people who are involved in various capacities are here. So it's good to see you, but it's also an invitation to everyone else who's interested in kind of higher order networks, data, dynamics to engage. We'll have a regular seminar series where we want to bring together the experts who are interested in this to learn from them. So if you volunteer to give a talk in our series, then please do get in touch. Otherwise, we'll approach you and twist your arm that you give a talk. So it's very good to mention this here, because this is the prime audience of people who might be interested in this. So this is starting from basically the fall onwards. And the positive thing is what Raffaella mentioned. We have our first publication, even though no PhD student has officially started yet. If this was all too heavy for you, then like look at this nicely illustrated book where we kind of introduce the concepts of well, networks, edges, and so on by bears that play soccer. And I realized after we talked about it, we need to add an additional, like we have the we have a picture there, or a drawing for hyperedges, and we have one for synchronization, but the synchronization is only pairwise synchronization. We don't have anything for hypergraph synchronization, and I think this is really lacking. So maybe that's one of the outcomes of this workshop, that we can try to conceptualize and the missing drawing. What is synchronization together with dynamics on hypergraphs? So with that, thank you very much for your attention. These are the references, and I have to acknowledge some funding. So yeah, I'm looking for more interactions in the coming days. So thanks.
Thank you, Chris, for this very dynamic talk. Are there questions? Everyone wants to drink. Jürgen?
If you look at correlations beyond synchronization and probably on hypergraphs, you can also find something that only emerges when you look at higher order hyperedges. Do you have any examples that?
I mean, the example. I mean, the standard examples are the kind of the simple synchronization dynamics, because you can say something about this. I mean, I briefly mentioned some work we did on chaotic dynamics that typically emerge from heteroclinic cycles, from these global bifurcations. That then, of course, since these are the systems that come from a phase reduction, should relate to chaotic dynamics in the nonlinear oscillator system. So basically saying that even though you have a collapse to an invariant manifold, if you have enough nodes, then you can see chaotic dynamics in these symmetric systems. So I mean, there's some examples out there, but looking at particular correlations between them, in this work we haven't done this, but higher order correlations are also part of the grant. That for sure. Yes.
Yeah, I have another question related to the one of Jürgen.
Yes.
And is these small motives that you do this effective order interaction, you get this higher order interaction that is being studied a lot from arenas and so on, but it's also true that this higher order interaction is linear in spirit, right? So it's similar to if you linearize the sine function, is similar to a Laplacian. So is it possible to get something else other than that?
Well, that's a good point. So I mean, like if you linearize this, well, that means you're interested mostly in like in the local dynamics around a specific state. So if you're interested in synchronization, then certain things collapse, right? The higher order structure, in some sense, then basically gives you potentially higher order corrections that may or may not affect the stability properties. But that's why we picked out this example of heteroclinic cycles, where the problem becomes a little bit more complicated, because you have to do simultaneous linearization around multiple states, and then basically also connect the global dynamics. So, and this is, I think, where it then gets interesting, because for that you don't look at you have to do simultaneous linearization of multiple parts of phase space, where then the higher order terms can give you more complicated dynamics. But that's a good point. Does that make sense?
Yeah, but you don't get anything more complicated than that in this approach.
I mean, more complicated.
Would you expect something if you have, 100 nodes? Would you expect something different from this perspective, or
so
that the linearized dynamics will always be linear? It will always be pairwise?
So the linearized dynamics, well, it doesn't always have to be pairwise, right? So also these type of, so I mean, this can also give contributions to the linearization. So your non-pairwise terms also contribute to the linearization of the system. Of course, that depends on how strong your interaction is. But I mean, you can almost see this from this thing, that the linearization of the first order dynamics are wrong for the nonlinear system. So in order to say something, to get the proper linearization of the reduced system, you should take second order terms into account, because they then, with the second order terms, you get a more correct linearization. Again, I didn't quantify the difference there, but the linearization here if you only look at pairwise interactions from a first order reduction is not correct.
My question, but unfortunately, most feel like education, because we know so much about parameter. But for instance, when I remember first time I read a little bit about it, was shocking. Differential equation, beautiful thing that it looks like Curie-wise transition curve is almost identical to gel. But kind of a little, if you think also similar curve for like Vrije or something. So in that case, you have one giant component, really, a lot of identities. But here you have a lot of this theta oscillators. They kind of form big region, and they essentially rotate, but they're not at the same point. That theta, these angles are not identical. And only those with large omega, largely different from average and channels, they kind of go up. So are there any models, maybe you can try to do something using this higher multiple interactions Chela, so that these oscillators really collapse into the core?
So I'm like the caveat is always that I look at identical oscillators. So basically, I'm in that sense.
So you just throw away.
So I throw away the heterogeneity in the most in most cases. So like in some sense, you can then do analysis if you're interested in large networks of identical networks on graph limits if you like, but the heterogeneity I typically throw away. Of course, if you go towards kind of a mean field limit, then the heterogeneity becomes another parameter that you have to track. That basically you write down a mean field limit that depends on the on basically two parameters, namely the location in your network. If you say, okay, well, you enumerate your vertices, then you have the spatial location, and then you have the intrinsic frequency of this, and that just makes the for mean field reduction, say, makes your probability distribution of your transport equation a bit more complicated. But like I kind of my background is more low dimensional symmetric dynamics, so I really like to think of symmetries. No, fair enough.
Okay, let's leave the other questions to the drinks and let's thank